So almost to reaching the quantum mechanical model, something that was really good historically to try to get us there with all the evidence that they had was this Bohr model of the atom. So that came about in 1913. So he had put together all the evidence that had come up to that point, which was what we talked about last time when I had like the wave-like behavior and the particle-like behavior they were describing. So he put together all this evidence to come up with this model. I want you to think about one of the first videos. We had this spectrum. We talked about the wave-like behavior with the spectrum of light. And we had this like from gamma up to radio waves. And there were different wavelengths in frequency in that spectrum. So within that spectrum of light, which they've known that for a long time, if you see a rainbow, then that's a spectrum of the visible range of light. So in 1862, so quite a ways before Bohr came up with his model, one of the most significant events was they had this hydrogen emission spectrum. So they had hydrogen and they electrified it and it emitted light. But it didn't emit like a whole spectrum. So it didn't emit like all the colors in the visible range. It only had 4 that they could see within the precision of whatever, spectral device that they had. So when they saw those 4 lines, they knew, okay, for hydrogen, there has to be some reason why there's all this spacing in between here. And they didn't know why. They just knew that there was something unique about why only those lines showed up. After that, so a lot of times we'll see things and then we'll try to get more precise measurements, and they try to come up with ideas of why that is, and then they argue with each other and dispute each other's claims. So at some point, mathematically, they can try to describe it. And with the mathematical model, so there's something called a Bohr series that we'll learn about. It's in the ALEKS homework. So the Bohr came up with this mathematical model which looked at these numbers. So these have, see how really small here, has a different wavelength. So there was particular wavelengths that these appeared at. So he was saying, okay, if I have these numbers of these particular wavelengths, there must be some way that I can relate them. So he came up with this equation, and in that equation he had different variables that he used in order to explain this. One of those variables that's in there, and you can see it in the textbook, is this variable n, which is what later on we're going to learn is part of the quantum mechanical model. So for n, and we still use this today, Bohr used it and we used it even though it's sort of an evolution of that, he found that that n only could have integer values. Those integer values are going to be our energy levels that we're going to talk about, and those energy levels are these different wavelengths that we saw. Alright, so this is going to give specific information on the Bohr model of the atom. So we kind of talked about that there was experimental evidence that he used to come up with this model. So he used all this evidence, and this is what he had. This isn't completely right, and I'll talk about maybe a little bit at the end what's not correct about it, but it gives some really good information that they built quantum mechanics off of. So this is not quantum mechanics yet, but this kind of relates to what he's going to do. Okay, so Planck, back in one of the previous videos, and this is Planck's constant, Planck gave this relationship between energy and frequency, and then we kind of had one that we came up with between energy and wavelength. So the idea for Bohr's model is you have light, And I put H nu here because that represents the energy of the light. So you have light come in of a particular energy into an atom. In the atom, we know there's the nucleus, and then the important part is there's electrons around the nucleus. This is often the picture that they show. If you look up the picture of an atom, it is not what it really is, but it kind of gives you more of a visual idea than the more complicated quantum mechanics. So the light comes in, interacts, this little dot here is what's representing an electron. Notice that the n values that we had from the previous video from the Bohr series, so these n values give you what Bohr's calling energy levels. So the lowest energy level is called the ground state energy level. When light comes in, if there's only one electron in the atom, so you can pretend like this is a hydrogen atom, then that one electron can get promoted or excited up to the next highest energy level. So you might want to write down some of these things I'm saying because I don't have enough room to write them. So light comes in, light in the form of energy. That energy is transferred to the electron. The electron, if it gets sufficient energy, it can transfer up or get excited up to a higher energy level. So it absorbs the light, higher energy level because it absorbed the energy from the light. Now it's from n equals 1, the ground state, to one of the excited states. So anything that's not a ground state is an excited state. So after that happens, that electron is not going to sit in a higher energy level, an excited state forever. It's going to come back down to whatever its ground state was. So if I have, say that electron now is up here, so same electron. That electron is going to relax back down, so we use the word relax back down, to the ground state or whatever its lowest energy level it can exist in. So for this one, it's n equals 1. So it goes back down to the ground state and it emits. So that energy from coming back down has to go somewhere. That energy comes back out of the atom in the form of light. So it comes back out as light. The light that comes out has energy that is the same as the energy of the transition. And that can be related, that energy can be related to the frequency of light that comes out. So this light that comes out has a particular frequency. That's how they took what Bohr did. So Bohr figured out there was those lines that they had on the spectrum, those 4 hydrogen lines, the color lines that I had over here. Those each represented a certain wavelength or frequency of light. That's because those were the energy level transitions that could happen or were allowed for the hydrogen atom. So let's come over here. This is the same idea, but it looks a little more like what you're going to see in the Alex homework and more in relation to like the quantum mechanical model. So let's do the same thing. Let's pretend like we have an electron in the ground state. On the Alex homework, I asked what the ground state is. The ground state is the lowest. They put letters on here, but these can also be related to, the n values that we have there, the energy level values. This is the ground state, which makes anything above it an excited state. Here's the possibilities for where that electron can go. So that electron can go from the ground state up to each one of these excited levels. But say this electron got here, it can go from 2 to 3 now. If something's at 3, it can go from 3 to 4. So for each one of these levels that it's at, it can go to the higher energy levels that are above it. So there's a total of 1, 2, 3, 4, 5. So 1, 2. Okay, so we have from the ground state, here, here, and here. Then you want to do from this energy level up. So we have from here to here. So we're missing here to here. And then if we look at this, there's only one place to go up. So one of the questions I ask is, like, how many absorption lines? So there's 1, 2, 3, 4, 5, 6 that are possible. So they absorb, and those are all the possibilities, but what you see is what's emitted. So then you would have same kind of the combination of them. You could have an electron up here, and it goes down. You could have one right here, goes down here, right here, goes down here. So you're still going to have 6 possibilities. It's just all, and it's kind of messy, but it's all the same combination. So when it's emission, they ask like the transfer, for different energy levels. So the transitions would be emission is D to C, or D to B, or C to B. If they say absorption, then that is where you go from A to B, or B to C, or A to D. So absorption is up, emission is coming back down. Emission is the one that you would be able to see or detect. So here's why this is what actually happens. This is sort of the crude model of it. What didn't work is once they got past one electron, there's this other, all these other things that could happen. The biggest thing, when it was more than one electron, and what was wrong, is they didn't consider the electron to electron interaction. So depending on how close, if you have more than one electron they're going to be repelling each other and pushing each other out different amounts. And then the other thing is, they said they moved in orbits, or Bohr said they moved in orbits, but it's not possible to know location. Of the electron and the momentum, or we'll just say the velocity of the electron. So the next thing we're going to talk about is finally getting into quantum mechanics, since we built up to this point.